Welcome. In this video we are going to discuss about titration of amino acids. Now amino acids have ionizable groups, and that is the reason why the predominant ionic form of these amino acids in a particular solution depends upon the pH of the solution. Okay, pH of the solution will determine in which ionic form the amino acid is going to be. And why is that? Because of the presence of these ionizable groups in the amino acids. Now titration of amino acid shows the effect of pH of the amino acid structure. Okay, what is the effect of the pH on the structure of amino acid? Okay, that we get to know by doing titration of amino acids. Now consider alanine, which is a simple amino acid. Alanine has two titrable groups, that is alpha amino group and the alpha carboxyl group. Now while doing titration of this alanine with a strong base such as NaOH, alanine loses its two protons in a stepwise manner. Okay, alanine loses its two protons in a stepwise manner while doing titration with a strong base such as sodium hydroxide. Now in strongly acidic solution, the alanine is present in that form in which the carboxyl group is uncharged. So in acidic condition, the alanine will be positively charged. Okay, so the molecule's net charge is +1 because the carboxyl group have no charge and the ammonium group is protonated. Okay, that is the reason why in strongly acidic solution, alanine, the net charge on the alanine is going to be +1. If the pH is increased, then there is deprotonation of the alpha carboxyl group, and then alanine will not have a net charge. Okay, and alanine will be electrically neutral. Okay, so the alpha carboxyl group is deprotonated and the ammonium group is protonated, so that balances the things out, and then this alanine becomes electrically neutral, and this happens because of increase in pH. So this is how it looks like. At low pH, the carboxyl group is uncharged. Okay, but as you increase the pH, the carboxyl group is deprotonated, and that is the reason why it becomes negatively charged. So this is negative charge, and there is on amino group there is positive charge, and that is the reason why the net charge is neutral. Okay, there is no net charge. And if you increase the pH further, then the amino group will become deprotonated and it will lose its positive charge. So at high pH, the alanine will be having a negative charge. So when the amino acid don't have any charge, okay, then that particular pH is known as isoelectric point. Okay, so isoelectric point is that pH at which your molecule will not be having any charge. Now because at isoelectric point there is no net charge, the amino acids are electrophoretically non-mobile, and that is the reason why they are least soluble at the isoelectric point. Okay, at this particular pH. Okay, so at isoelectric point, the amino acids are least soluble. Now if you further increase the pH, that is if you lower the proton concentration in the system, then the deprotonation of the charged amino acid will take place. The charged amino group of amino acid will take place, and the deprotonation of charged amino group will result in the formation of uncharged amino group. So at high pH, the net charge on the molecule becomes -1. So at high pH, the ammonium group is deprotonated and the net negative charge develops because of the presence of carboxylate group. Now this figure is showing the titration curve of alanine, which is a monoamino or monocarboxylic acid. Okay, so this curve is a titration curve. Now a plot which shows the dependence of pH on the amount of OH- added, then that plot is your titration curve. Okay, so this is showing the dependence of pH upon the amount of OH- added. Okay, this axis shows the OH- equivalents and this axis shows the pH. So as you add the concentration, or as the concentration of OH- increases, the pH also increases. So the isoelectric point of alanine is calculated by this equation, that is Pi is equal to pK1 plus pK2 divided by 2. Now for alanine, pK1 is 2.34 and pK2 is 9.7, and that is the reason why the isoelectric point for alanine is 6.0. Now amino acids which have ionizable side chains, for those amino acids the titration curves becomes more complex. For example, glutamic acid, which has a carboxyl side chain group. Okay, for this type of amino acid, the titration curve will become more complicated. Now at low pH, the net charge on the glutamic acid will be +1. Now as base is added, that is as pH increases, the alpha carboxyl group loses its proton and the carboxyl group gets converted into carboxylate group. Now this glutamic acid has two carboxylate group or two carboxyl group. Okay, one is in its side chain is there, right? One extra one. So it is called as polyprotonic acid. And in case of polyprotonic acid, the protons are first lost from that group which has the lowest pKa value. Okay, so as the glutamic acid has two carboxyl group, now which one of them is going to lose proton will depend on the pKa value. Whichever has the lowest pKa value will lose the proton first. So at this point, when you lower the pH and the carboxyl group loses a proton and becomes carboxylate group, there is no net charge on the glutamate. Okay, but when you add more base, okay, you increase the pH further, the second carbonyl group loses its proton. Okay, it is a second carboxyl. So as you add more base, the second carboxyl group also loses a proton, and then you have a net charge on the molecule -1. Okay, -1 charge is there. And if you add base further, then there is loss of proton by the ammonium ion, and now the glutamate has net charge of -2. So you start with +1, then you add pH, you add base, you increase pH, then you go to 0, then you increase pH, then you go to -1, and after increasing pH even more, at last you will get net charge of -2 on the glutamate. Okay, so this is how it looks. At low pH, the net charge on the glutamate, okay, glutamic acid is +1. and the pKa1 value is 2.919. And as you add more base to it, as you increase pH, the carboxyl group is deprotonated, and that is the reason why it becomes negative. And now you have no charge on this molecule. But if you increase the pH further, then the secondary carboxyl group also loses a proton, and now there is net charge of -1 on this molecule. But if increase pH even further, then the proton of the amino group is also lost, and now you have -2 charge on the glutamic acid, okay, at high pH. So the amino acids which have ionizable side chain, which have ionizable R group, have more complex titration curve, and the 3 stages corresponds to 3 possible ionization steps. Okay, and that is the reason why in this case there are 3 pKa values which are referred to as pKa1, pKr, and pK2. Now the Pi value for glutamate is the pH that is halfway between the pKa values for the 2 carboxyl groups. Okay, so Pi, when you put the value of pK1 and pKr, then you will get the value of Pi as 3.22. Now consider histidine amino acid. Now this amino acid has imidazole group, which is an aromatic ring which is positively charged. So positively charged aromatic ring, that is imidazole group, is there in your histidine. Now with the pKr value of 6, the imidazole group can be readily ionized near the physiological pH. Okay, so the imidazole group of the histidine can be uncharged or it can be positively charged at the physiological pH. Now histidine is found in the active sites of the enzyme, where the imidazole ring of this histidine bind to release the protons for enzymatic reaction to occur. Okay, if a particular reaction requires a proton, then the source of the proton is the imidazole ring. Okay, it can be imidazole ring of the histidine. So at the active site of the enzyme, if you are finding histidine, then its function may be to release a proton from the imidazole ring, so that the reaction for which the enzyme is there can occur. Now because of the fact that the pKr values of the histidine is near 6, only histidine act as the significant buffering power at neutral pH. Okay, only histidine provides significant buffering power at neutral pH. And why is that? Because its pKr value is near 6. Now let's see the stepwise dissociation of fully protonated histidine molecule with the help of a figure. So this figure is representing the titration of histidine. Now at very low pH, the histidine molecule have +2 charge. And why is that? Because the amino group has a positive charge, and this imidazole ring also has a positive charge. And because of this, the overall net charge on the histidine is +2. Now as you add the base and you increase the pH, the carboxyl group becomes deprotonated, it loses a proton, and now the net charge on the histidine becomes +1. Now you will increase the pH by adding the base, and after that what happens is the charged imidazole group loses its proton, and now the overall charge on the histidine molecule is 0. Okay, there is no net charge. And if you increase pH further, then the proton of the amino group is also lost, and now you have the net charge as -1. Okay, so that is how the titration of this histidine molecule looks like. You start with +2, then +1, 0, and at last -1. Now, according to Bronsted concept of acid and bases, the acid is a substance that donates proton and base is a substance that accepts proton. Now consider this generic acid Ha. Okay, when this acid donates its proton to water, then one of the product of that reaction is A-. Now this A- serves as proton acceptor, or it serves, or you can also call it as Bronsted base. Okay, so when an acid is donating a proton, then it acts as a base. Okay, so every time a Bronsted acid acts as a proton donor, it forms its conjugate base. Okay, so if you consider Ha as acid, then A- acts as the conjugate base. And when this A- will accept a proton, then Ha will be your proton donor or Bronsted acid. Okay, so when base gains a proton, then that results in the formation of conjugate acid. Okay, so consider this reaction. Okay, this acid reacts with a base, and that results in the formation of this conjugate acid with respect to this base, and there is formation of this conjugate base with respect to this acid. Now this ionization of an acid can be written as a simple dissociation as this equation. Okay, Ha gives us H plus A-. So acid dissociates into its component ions, but these ions then reassociate together to form the original acid again. And if the rate of dissociation is equal to rate of association, then we say that the system has achieved equilibrium. So if you call an acid a strong acid if it dissociates completely, and on the other hand the weak acid does not dissociate completely. It means in case of weak acid, there is low percentage of molecules which are in the dissociated state. Now the concentration of acid at which equilibrium takes place is known as dissociation constant Ka. Okay, dissociation constant is the concentration of acid at which the equilibrium occurs. And this dissociation constant is a quantitative measure of the strength of acid in a solution. Okay, so if you want to find out what is the strength of a particular acid, then you should look for its dissociation constant. Okay, so this equation is representing your acid dissociation constant Ka, which is equal to concentration of protons into the concentration of the conjugate base divided by concentration of acid. So if more protons are there, it means the acid is more strong. That we can conclude logically. Now the measure of this dissociation constant Ka for the weak acid is given by its pKa value, which is equivalent to negative logarithm of the dissociation constant. So pKa is minus log of Ka. That's all for this video. Thanks for watching.